Today we're going to revisit the extreme value theorem. In order to do so, let's first review some concepts of compact sets and functional limits. We'll begin with the Heine-Borel theorem that says that the following three statements are equivalent for any subset K of the real numbers R. First, every sequence of X sub n's contained in K has a convergent subsequence where the limit of this subsequence is an element of K. Second, K is a closed and bounded set. And third, every open cover of K has a finite subcover. That is, if there exists a family, O sub lambda, of open sets such that K is contained in the union of the O sub lambdas, then there exists a finite collection of indices such that K is the union over the O sub lambdas of this finite collection of the subscripts lambda. Any subset K satisfying either of these equivalent definitions is said to be a compact set. We have the following two statements as a corollary. First, let's say that K sub lambda is a family of compact sets. Then its intersection is also a compact set. Second, say that we have a finite collection of compact sets. Then its union is also a compact set. We have the nested compact set property that says if we have a collection of non-empty compact sets K sub n such that K sub n plus 1 is contained in K sub n, then the intersection is also a non-empty compact set. Finally, we have the following three statements that allow us to define the limit for a function. Say that we have a closed interval I and f a well-defined function on this closed interval. Then the following are equivalent for any point P in our closed interval between A and B. First, we have the epsilon delta criterion that says given any positive epsilon, there exists a positive delta such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus P is less than delta and different from 0. Second, we have the topological criterion. This says for any open neighborhood V sub epsilon of L containing some real number L, there exists an open neighborhood V sub delta of P containing our point P, yet contained in the closed interval I, such that f of x is an element of the first open neighborhood V sub epsilon of L whenever x is an element of the next open neighborhood V sub delta of P and x different from P. These two are equivalent to the sequential criterion. This says that we have the limit as n increases without bound of the sequence f of x sub n equals L for all sequences A containing our x sub n, where x sub n is contained in I, x sub n is different from P, and P is the limit of the x sub n's. If either of these equivalent statements holds, we'll say the limit as x tends to P of f of x equals L. We have the following corollary that explains how to compute the limits if we have the sum of functions or the product of functions. Let's say that I is a closed interval from A to B and choose a point P between A and B. Let's say that f and g are two well-defined functions on this closed interval I such that the limit as x tends to P of f of x is L sub 1 and the limit as x tends to P of g of x is L sub 2. We have the following two limits. First, the limit as x tends to P of r times f plus s times g is r times L1 plus s times L2 for any constants r and s. Second, the limit as x tends to P of f times g is L1 times L2. We also have the divergence criterion that explains when a limit does not exist. Say that we have a function f defined in a closed interval and that we have two sequences, capital A in terms of a lowercase a sub n and capital B in terms of a lowercase b sub n, such that three things hold. First, the limit of a sub n equals the limit of the b sub n equals P. Second, no an and no bn equals P. And third, the limit as n increases without bound of f of a sub n is different from the limit as n increases without bound of f of b sub n. Then the limit as x tends to P of f of x does not exist. We're going to use all of this so that today we can discuss continuity, but do it in a slightly different way. Our main theorem is as follows. Let's say that I is a closed interval and f is a well-defined function. Then the following three statements are equivalent for any point p in our closed interval between a and b. First, we have the epsilon delta criterion. That is, given any positive epsilon, we can find a positive delta such that the absolute value of f of x minus f of p is less than epsilon whenever x minus p is less than delta. You'll notice that this is different from what we said before because now we are not assuming that x is different from p. In fact, now we allow x to equal p. Next, we have the topological criterion. This says for any open neighborhood v sub epsilon of L containing L which is defined as f of p, there exists an open neighborhood v sub delta of p contained in our closed interval I, such that f of x is an element of v sub epsilon of L whenever x is an element of v sub delta of p. Third, we have the sequential criterion. This says that the limit as n increases without bound of f of x sub n equals f of p for all sequences A containing x sub n, such that x sub n is an element of our closed interval I, and the limit as n increases without bound of x sub n equals p. If either of these equivalent statements holds, we'll say that our function f is continuous at p. Indeed, in the past, we've already seen that our definition of continuity is the same as the epsilon delta definition. In fact, we proved as a consequence that if f is continuous, then the sequential criterion holds. Now we claim that the converse is true. That is, if the sequential criterion holds for all sequences, then the epsilon delta criterion holds. Today we'll spend a little bit more time discussing the topological criterion. For the proof, really this follows mutatis mutandis, that is, pretty much the same way that we did the proof in the previous lesson when we defined limits. Now, we'll just write things in a slightly different way by choosing our limit L to be f of p. As a corollary, we have the following result. Again, say that I is a closed interval and f is a well-defined function on I. Then f is continuous if and only if the inverse image f minus 1 of an open interval O itself is open. Simply put, the inverse image of a continuous function should send open sets to open sets. We should point out that the function f minus 1 really doesn't exist. Here, we just simply use notation. By preimage, we mean f to the minus 1 of a set O to just mean the set of elements x in the domain such that f of x lies in our set O. First, let's assume that our function f is continuous. We'll prove that the inverse image of an open set is always an open set. To this end, let's choose an open set O. In order to show that f minus 1 O is an open set, we'll pick a point P in f minus 1 O, and we're going to show that there exists a positive delta such that v sub delta of P is contained in f minus 1 of O. Since P is an element of f minus 1 of O, we see that f of P is an element of O. But since O is an open set, we can find a positive epsilon such that v sub epsilon of L is contained in O, where here L is just f of P. But the topological criterion for continuity says that now there must exist a positive delta such that v sub delta of P is contained in I. But notice that this means that f of x is contained in v sub epsilon of L whenever x is contained in v sub delta of P. So using the definition of continuity, we now see that the definition of our preimage, we see that v sub delta of P really is contained in f minus 1 of O. This means that f minus 1 of O is an open set as we claimed. Conversely, let's assume that f minus 1 of O is an open set whenever O is an open set. We're going to prove that our function f is continuous. Let's pick a point P in our closed interval between A and B. For any positive epsilon, we'll define an open set O to be v sub epsilon of L, where L is f of P. then by definition, P is an element of f minus 1 of O. But since our choice of O is an open set, and we know by assumption that f minus 1 of O is an open set, this means that around the point P, we can find a positive delta such that V sub delta of P is contained in f minus 1 of O. But then this means that f of x is an element of V sub epsilon of L whenever x is an element of V sub delta of P. The topological criteria for continuity now says that our function f must be continuous at this point P. Let's try to discuss an example and a non-example of this concept. For the moment, let's consider the quadratic polynomial f of x equals x squared. We know that this is a continuous function. In order to make sense of the previous proposition, we must take a look at pre-images. So for example, let's say that K is just the singleton set consisting of one real number L. Then f inverse of K simply means we're trying to find the numbers x such that x squared equals L. Well, if L is negative, we know that there are no real numbers such that x squared equals L, so we would see that the inverse of K in this case is just the empty set. When L equals 0, there's only one real number x such that x squared equals 0, so we see that f inverse of K in this case is just the singleton set consisting of 0. Finally, if L is positive, we know that there are two real numbers x such that x squared equals L, namely plus and minus the square root. So in this third case, we actually see that f inverse of K consists of two elements. In particular, we have the following examples. Let's consider the open interval from -1 to -4. In this case, all of our L's are negative, so f inverse of this open interval is the empty set. The empty set is still an open set. Next, let's consider the open interval from -1 to +1. Now, we'll have to consider the L's between -1 and +1, but of course, the only L's that are really of interest would be the L's greater than or equal to 0. So in this case, f inverse of this open set is the open interval from -1 to +1. Again, this is an open set. Finally, let's consider O to be the open interval from +1 to +4. All of our L's here are positive, so f inverse of this open set consists now of two open intervals, namely the open interval from -2 to -1 and the open interval from +1 to +2. But this again is an open set. As a non-example, let's consider the so-called Heaviside function. This is a function h where h of x is 0 whenever x is negative, and h of x is 1 whenever x is greater than or equal to 0. Let's consider the open interval from 0 to 2. Then the inverse image is the half open interval from 0 to infinity, where we contain x equals 0. Indeed, if x is greater than or equal to 0, then h of x is 1, and 1 is an element of the open interval from 0 to 2. In particular, the inverse image of this open interval is not an open set, so we see that the Heaviside function is not a continuous function. Next, let's talk about what happens when we consider continuous functions on compact sets. In fact, up to this point, we've really focused on functions defined on a closed interval I from A to B, and of course, our closed interval from A to B is an example of a closed and bounded set, which is just the compact set. So we'll generalize now for any compact set K. Let's say that I is a closed interval and f is a continuous function. We'll let K be any compact set. First, we have the boundedness theorem. This says that the image, namely the set of elements y, such that y equals f of x for some x in K, is also a compact set. Simply put, this function f, when restricted to a compact set, is a bounded function. Next, we have the extreme value theorem. This says that there exists numbers c and d in K such that f of d is less than or equal to f of x is less than or equal to f of c for all x in our compact set K. That is, our function, when restricted to a compact set, attains both its maximum and minimum values on this compact set. So here we have a generalization of two theorems that we've considered all along. But now we're considering our function not just on closed intervals I, but we have our function f on any compact set K. Let's explain the proof of this theorem. We're going to show the first statement by showing that every sequence contained in our image S has a convergent subsequence whose limit is also contained in S. This was one of our criteria for showing that a set K is compact. Since our sequence capital A is contained in our image S, we can find a sequence x sub n containing K where our y sub n in capital A is equal to f of x sub n. But capital K is compact, so there exists a subsequence x sub n sub k where its limit p is also contained in K. Let's choose capital B to be our desired subsequence in terms of y sub n sub k, where y sub n sub k is just equal to f of x sub n sub k. But now, since capital F is continuous, the sequential criteria for continuity shows that our limit L is f of p. But since p is contained in capital K, our limit L must be contained in S. Now let's show the second statement. We know from the first statement that our capital S is a compact set, so it is closed and bounded. We simply have to show that we can find our maximum values for F. Since S is bounded, let's denote lowercase m as its infimum, that is greatest lower bound, and capital M as the supremum, that is least upper bound. Since S is closed, we see that lowercase and capital M are both elements of S. This means that there exists C and D in capital K, such that capital M is f of C, and lowercase m is f of D. In particular, f of D is equal to m is less than or equal to f of x is less than or equal to capital M, which is f of C for all x in our compact set K. But this is exactly what we wanted to show. Thanks very much for watching.